So I think without further ado, we're going to have, I said 5 minutes for each of the presenters. So they get 4 or 5 minute head start to talk, and then people can ask questions, maybe 2-3 minutes, and then we'll move on to the next session. And I'll stand more aggressively to the side of the stage as the time expires. Okay. So the first talk, Alex, do you wanna come up? Can I start?
Okay, good afternoon. This is a work in progress that we are doing in Federal University of Pará in Brazil. I will try to explain really fast what we're trying to do. Although it's difficult to introduce large chains on traditional schedulers, we can see in Swift work that by analyzing the process behavior, we can adjust, for example, the priority and quantum in a more dynamic way. Because Swift's work motivates our research on process schedulers, we decide to use the same operating system used by Swift, in this case Minix. The other point is that we are also using Minix in some embedded systems because of its fault-tolerant issues. This operation system has a microkernel structure and uses mesh to allow process communication. However, microkernel-based operation systems, such as Minix, have particulars that need to be considered in process scheduling tasks. For example, most of the servers of the systems runs in user level, and the impact that the design of the inter-process communication have in the execution time. Considering the process scheduling modularity of Minix microkernel layout, we think that the best approach is to treat each process scheduler as an object. In this paper, we choose the feedback scheduler and propose an object-oriented model with a small interface to communicate with the other servers of the system and with the kernel. To understand how the process scheduler works in Minix, we have to consider the way that the server and the kernel communicate. In the first figure, it shows how the scheduler receives messages from other servers and the kernel. Each arrow in the first figure is tagged with a number that identifies which type of message they could send to the scheduler. For example, start, stop, nice, no quantum. Swift proposed 2 system calls to enable the communication between the user space, process scheduler, and the small scheduler interface that belongs to the kernel, the second figure. The first system call is sysschedule and is used by the scheduler to request the control over a specific process. And the other system call is sysschedule, and it's used when the scheduler needs to send the basic information that is used by the scheduler interface. To better understand the original code of the feedback scheduler, a diagram was done to represent the flow between each function. In this figure, you can see the communication between the structured functions. The main function is an infinite loop that waits for a message coming from the other process or even the kernel. When a message arrives in the scheduler, it has to choose between one of the following message functions: start, init, stop, nice, or no quantum. Then, each one of these message functions can call other functions, some of them with unique use as a message function, and most of them share the use between the other's message functions. For example, this figure shows that the stop function just uses 2 functions, accepted message and scad is anti and pt, both shared with nice function. On the other hand, no quantum uses 2 shared function, scad is okay and pt, schedule process, and one with unique use, burst mode. As mentioned before, one of the main goals of Minix and other microkernel operation systems is to provide modularity. Thus, we decide to deal with the process scheduling using the object-oriented model instead of the structured model. For example, in the structured programming approach, when the scheduler receives a message from the user program, for example, nice, through the process manager, it identifies the nice message and calls a specific function associated with this message. This function will identify the number of the process using the endpoint and will check if it's valid to adjust the priority of the process. After this, the user level scheduler has to communicate with the kernel using the system call described before to inform that they have to change the priority of the process. We believe that it's better to deal with this as a method from a class, because when we think about a modular system, it is difficult to conceive a process individually and then have a couple of functions to deal with each specific situation. We propose the following class, the first figure, to deal with every process on the system. This class has all the original variables as extractors and all the separate functions as methods. If you consider the example of nice program, we notice that by using this model, it's much easier and rational to deal with a process. Comparing with the older model, we have the original value of the priority as an attribute, called priority, and then we just call method to adjust this value to a new one. To make things work with this new approach, we implemented a small piece of code to interface the new scheduler with the other system components. We call this decoder. This decoder, second feature, is basically responsible for receiving messages from other parts of the system and considering the process that is going to be changed, access a specific position of the vector of objects from the class scheduler. Thank you.
Questions? Comment?
Sorry for my English, I'm trying to improve.
No, it's very nice, very nice. You said in your in what you submitted, you teach. You use this to teach.
Yes, the points that USENIX motivated me to do the master degree and PhD, but in another field. And past 2 years, we tried to start using USENIX not just for teaching purpose, but in embedded system after they ported to BeagleBone. And then we decided to work with the scheduler. We're thinking about this, but we are just starting. We are the beginning of our research.
I see. Okay, good.
Thank you.
Beautiful. Thank you. Thank you so much, Alex. Still upset at me. Okay, so Aaron is next. I'll bring up his slides. He's going to burn power for fun and profit. And my laptop's not plugged in, so it better be not a lot of power.
All right, thank you. So I'm going to show you how we can use this weird feature of multi-core CPUs to maybe improve performance, but burn an unethical amount of power. And so I actually discovered this by accident when I was working on a project trying to actually save power. And the idea was, okay, you got a bunch of threads, you got a bunch of CPUs. Maybe if I run those threads on a small number of CPUs, switch off the unused CPUs, we can save some power, right? That's an old idea. I was just sort of toying with it. And what you want to know is, how expensive is it to do the operation, the key operation here, which is take a thread and move it to a different CPU, okay? Or a different core in this case. So, okay, set up an experiment where you have a thread and you're moving it around a bunch of cores. And let's say every 10 milliseconds you migrate it to a different core. And then you plot the result on a graph that looks a bit like this. And you go, well, all right, 5 to 20%. It's not great, but we can deal with that. But the problem with confirmation bias is evident here. I was expecting to see a slowdown, and that's what my brain saw, but actually 15% negative slowdown is a speed up. Great. I made a mistake somewhere. My calculation was wrong, or I screwed up the code. Something went wrong here, so obviously I went back and I spent a week or two looking at this thing, even to the point where I had an actual stopwatch out going, all right, run the benchmark, time, wait, time. It's actually getting faster. Something is going on here. And it's true, you actually get a speed up, and I'm going to explain why. So some CPU architectures have this nice thing called a cache-to-cache transfer. And the way it works is you take a miss in an L1 cache, the purple line, and you need to refill that cache line, right? And there are two options. You can either pull it out of the L2, or if you're lucky, that cache line happens to be in one of the other L2s, you pull it from there, and if it's faster than going to the L2, you've got to speed up, okay? So the idea is you run your thread on one of the cores, and you let it populate the L1 there, and then a little bit later you move it to the other core, and you run it there for a bit, and then you move it back, and then you move it back, and then, so you're sort of spreading out the working set over the caches of all the cores on this CPU, right? You're smearing your working set, giving you an L1.5. It's faster than an L2, but it's smaller, but it's slower than L1, but it's larger. Okay, so here's how we do it. You take your single-threaded program and you run it on one of your cores, and you spin up a bunch of threads, one on every other core you've got. And you put them into a loop, waiting on this current CPU thing, which is the token. This is the who's allowed to run the thread right now. And your actual application is running there, and you set up a timer, let's say every 5 microseconds. The timer fires. You jump into the kernel, you take an IRQ, and in kernel mode, you take the state of the current CPU, the current thread, and you just dump it somewhere into memory. Then you toggle the current CPU thing, and you say, hey, your turn to run. This guy's just sitting there in a really tight spin loop, waiting for his turn, sees that, oh, it's my turn, grabs the state, and does this sort of half user space, half kernel space thread switch. This is super fast, right? Because you've got, on the right side there, you've got a kernel entry, so a mode switch, an IRQ delivery, a bit of cache coherence, a bit of memory reading and writing, but basically there's not much going on here, so you can do this super fast. Okay, so we have a nice mechanism to do this. What kind of speed up can you get? Well, if you tune it just right, you play with all the parameters, you design the workload that exactly works here, you get a 70% performance improvement by using 4 cores. But of course, you have CPUs sitting there in a tight loop, you're burning a huge amount of power. And in fact, on the device, this only works on ARM, actually, because x86 doesn't have this nice thing. That's a detail, but you can't even do this on a phone, right, because you just burn so much power that you can't sustain it. Okay, so that's kind of cool. If you tune the parameters, your porridge is just right, you can get this nice 70% speed up. What do you get in real life? And the amazing answer is pretty much nothing. So Spec 2000, Spec 2006 gives me a lovely 0%, which is better than negative, which is what you'd expect, right? But it's not great. And there's a few reasons. One is, as soon as you write to a cache line, it invalidates it everywhere else. So you need a workload where you never write anything, or at least not very much. You need the cache-to-cache transfer time to be less than the L2 access time, which is true on Cortex-y kind of ARM embedded, not true on x86. And you really need the working set to be right in the sweet spot, which is bigger than L1. If you're not missing an L1, obviously this is not going to help you. But if it's too big, then it's not helping you either, because the differential in the cache miss cost is not that much. So have you seen this workload? I would love to find something which is not, I hand-tune this for a week to get 70%, because that's not really a very interesting argument, but it's got to be out there somewhere. So let me know. Thank you.
Thank you, Aaron. Hold on a second. Hold on. Let's see if anybody has any questions. Go ahead. We got some time. Go.
So have you tried it on an AMD? Because the AMD chips have a really strange CAS architecture inside that might be a little bit more similar to the ARM.
I have not. That's a very good point. I will not do that because I'm no longer a grad student. I don't have time to burn. But but I'll put the code on GitHub and somebody else can give it a try. But the detail is that on x86 Intel, at least, the migrations go through the L2, right? So you don't get anything on Intel. But if it's not the case on AMD, it could totally work.
So on a smartphone thing, how fast could it run down the thing? Could I start, like, put it in the little USENIX app and then run people's phones down so they keep listening late in the session? Could I use it like that?
Maybe. So if you really, really care about performance for like a few seconds, maybe this will fly. But on the experiment that I ran, after about 2 minutes or something, now you're hitting thermal shutdown.
Yeah, I don't know. So that was my goal. Yeah, that was my goal. How quickly to get
There's some ways to go yet.
Thank you. Anybody else? Comments? Thanks a lot.
Right,
Thanks a
cheers.
lot, Eric. What's that? No. I started at 100%, and I'm fine. What was that? I'm not using all my cores, no. Not with you guys. What do I do? This one.
Hi, I'm Joe Tuchek. I'm here to tell you how nobody survives the machine. No, not this machine. I'm talking about this machine. Now, maybe many of you know that HP has this big project called the Machine, with new computer architecture, new systems architecture. And you say, well, you know, the guy from HP is going to say that everybody is going to have to go through the machine. You know, I'm from HP, and of course, we're going to have to go through it. My point is partially, you all are going to have to go through it as well. Everybody is going to go through this. Nobody will survive the machine. So what is the machine? Now, the machine is it's HP's particular envisioning of what hardware is going to have to look like given 3 trends. 1 bad trend and 2 good trends. So the bad trend is we're going to have to use lots and lots of energy efficient cores. And the 2 good trends are we're going to have lots and lots of byte addressable NVM, and we're going to have really, really high speed, low latency interconnect between it. And you might say, well, that sounds interesting. Why do I think this is so? Well, let's go through. All right, CPU. All right, single-threaded scaling is dead. Dennard scaling is dead. You are going to get the single-threaded performance you have today, maybe a little bit more. We're already power per core limited, and that's basically the only way we're going to get more single-threaded performance. We can't burn more power. The only way to get more performance is to go to more cores. Second thing, lots and lots of byte addressable non-volatile memory. I'm from HP, I love Memristor, but you know, I said you don't have to use HP's machine. You're going to be using a machine that looks like it though. You're going to have some phase change memory, some spin torque, maybe one of the other RAMs. The major memory manufacturers are desperately searching for something to carry them beyond flash and carrying them beyond the scaling limits of DRAM. So it is coming. The only question is when. And regardless, disk is already too slow. You know, even today, you know, I can get a 6 terabyte disk and I can't touch my data. So we are going to have to move our computation towards something that is a lot lower latency and a lot faster, a lot higher bandwidth. And then finally, really, really high speed interconnect. Now, silicon photonics is nice. It's becoming a lot more practical, cheaper. But you don't even have to believe me on that. Today, you know, all right, RDMA and high-radix switches, oh, that's an HPC thing. That's not an HPC thing anymore. Yeah, you can get enterprise NICs, enterprise switches that run Rocky that can do this low latency access to memory in a large set of machines, and it's something you can do today. It's already here. So here's the decent thing: it's one bad trend. You're not going to get single-threaded performance, but it's 2 good trends. You're going to have much better I/O. So what does this mean? What do you have to worry about? What do you have to do to survive the machine? Well, you need to worry about your CPU utilization. You need to worry about spending cycles per byte. I have 2 little graphs up here. The one is, you know, we ran the same benchmark on Spark, and we did it in C++. So it's the same machine, 60-core machine, and the sequential C++ program is a little bit faster than the 60-thread Spark. We weren't trying to cheat. We optimized that Spark later as well as we could. We got it down to about 20 seconds for that workload. And then I threw a little up in MP at my C++ and got it down to 2. We can't afford to be spending a whole bunch of time on nice languages. Similarly, we can't spend a lot of time on I/O. The dark blue bar is the traditional Spark data transfer code. The red one is one that we optimized to take out a bunch of this excess CPU utilization. It's about a factor of 2 performance improvement by doing that. What? Yeah, because I want to write my program eventually. I can't use assembler. So the other thing I want to say is you can start worrying about this today and start finding out what other little picadillos there might be, even for big data, because most big data isn't really all that big. I've never seen a graph data set that was not synthetic, that was bigger than 500 gigabytes. Now, there are some people, I know there's the Facebooks and the Twitters that probably have a bigger data set, but most of us are the GMs or the eBays or the USENIXs. We don't have huge, huge graphs. You might say, oh, it's special hardware. And you're right, you can buy some special hardware that gets really big. Oracle will sell you a 32 terabyte memory machine. HP will sell you a 24, and IBM will sell you a 12 terabyte machine. You can also go to an OEM white box vendor like Quanta, known for making the cheapest no-name boxes ever. They will sell you a machine, cached on the barrelhead, that has 3 terabytes of memory in it. So you have no excuse not to be, prepared when it finally happens that you can't afford to spend time on your I/O, you can't afford to spend time on your network, you got to worry about your CPU.
Just a quick question about what you consider the workload that this is true for, because I work at Comcast, and our workload is entirely high-level languages because of programmer productivity. And so I'm just kind of curious. A lot of what you described sounds kind of like HPC type stuff, where you care about one giant data set and so on. But I mean, when you talk about GM and so on, I mean, IT is not that, and people are not going to spend time hand optimizing parallel C++ or whatever. So I'm just kind of curious as to whether you think this is a general architecture that will solve all of IT's problems, or?
So there's two sort of approaches. You need to either make those programmer productivity languages more efficient, or there will be cases where you find a kernel where you're just going to have to spend a little bit of programmer time. I think even for, say, like, an ordinary use case would be, what if I'm looking at all of my customer logs, all the packet latency that I measure as it goes through, and I'm going to do analytics to find fault before it happens. That is an awful lot of data. It's not something you do today, per se, but it's something that could be very valuable to do if you had the frameworks and the memory in order to do it.
All right, thank you.
And now I'm going to get grilled for something.
Yeah, I mean, sequential programs are really easy to write, but they're full of bugs and kind of have crappy reliability. Parallel programming is, orders of magnitude harder.
Yes.
And you're saying now the future is get used to having 1,000 cores or whatever, because that's the way it's going to be. How are you ever going to program that stuff and make it work?
I have no idea.
Yeah,
All I know
me
is you are not getting multiple, more single-threaded CPU.
Quick, where do you see cache consistency in that picture?
So one thing that's a very good idea, a good point, is that a cache consistency at a very large scale is very difficult. So I will admit that 32 terabyte machine is probably cache consistent. If you want to go really big, I mean, we'll probably be able to do cache coherent at 32 terabytes for much more cheaply in the future. If you want to go to a petabyte, probably not going to be coherent.
Thanks, Jeff. Thanks, Andre. In case people remember where we are, Tom Coughlin, storage guru, and Svengali. Hopefully that's not out of line.
Uh-oh. You find it?
Yeah. It's still open.
Go to the front.
And thing.
Oops. That's the end.
Yeah, it's thinking about it.
Thank you. There we go.
Ah! So many buttons, so little time.
It always does that when you're watching.
There you go.
All right, thank you. So, thanks. So I'm going to talk about some work. There's actually a fellow named Stephen Hetzler, who's a fellow at IBM, And he did come up with this idea that I'm going to talk to you about in just a few minutes. And so we put together a white paper on it, but we're still working on this, so it is a work in progress. So I'm going to talk to you a bit about that. So first, a couple of definitions. This is key to what this thing is about. The first is what's called touch rate. It's the portion of the total capacity of a given storage device or system that can be accessed in a given interval of time. For instance, here we give an example of what that might look like for the touch rate for a year. Now, the second item, and we're going to plot these two together, that's where it becomes interesting, is the response time. That's the time to complete an I/O operation. It includes the transfer of data and restoring the system to do more I/Os. And it's therefore a function of the object size, the thing you're moving around, as well as the speed of all the support operations that make that possible. So here's this basic chart, interesting chart here, which is charting a log of the touch rate per year here, and the response time. It could be per year, it could be per month, it could be per day, whatever it is. And also a plot of the response time. We're also showing some important characteristics for storage devices and systems. For instance, how accessible the data is, how much it costs per storage capacity, and how fast it is. And we're also showing various sorts of performance regions, from a high IOPS region to a transaction region, not quite as high a performance, to nearline, semi-active, a cold active, and an inactive region. And all these things can be seen as tiers of storage. Now, we can also plot different storage technologies, and we get these sort of these peculiar shapes here, which has to do with the size of the objects for these different types of devices, and the trade-off between touch rate and response time. So here's flash memory, performance hard drives, capacity hard drives, and here's tape. A little later on, I'll show you an example where we're also showing optical storage in there, just because there's some interesting things being done with that. So if we were to plot a storage device on here, for instance, here's a capacity 4 terabyte hard disk drive, and we're showing for the size of the objects here. Let's see if this works. We're showing for the size of the objects what the response time is, and what the resulting touch rate is. And you can see, for instance, if we have small objects where the access time dominates, the touch rate tends to be less, but we have higher performance as you go to larger objects with this device, and this is the general trend for devices. You'll get faster. You'll be able to touch more of the data on the device within that period of time, but your performance will go down. So, for instance, for this a 4 kilobyte object, the response time is 13 milliseconds. The touch rate is 2.4 times per year. So if you go up to a larger size, for instance, at a 64K object, right over here, at a time increased slightly to about, the touch rate has grown to 37, the response time increased slightly to 13.4. If you go up to 1 megabyte object, the touch rate is 412, and the response time is increased to 19. And after that, basically, you get into this touch rate saturation region. You're dominated by the data transfer time, no longer by the access time. So that's basically how all these things work, and it's an interesting way of looking at this. Now, if we were to look at a few different devices here, for instance, here's that nearline hard disk drive again. Here's optical disks, and here's magnetic tape. So the optical disk has a higher touch rate, which is because of the random access of the disks. All this depends, of course, for these devices, because it's a removable library, so it has to do with library characteristics, how many drives per disk, how fast the robotics is, etc. But we find, you can see that indeed the hard disk drive works well on that near line. That's sort of a sweet spot. And by the way, the best spot tends to be where the knee of the curve is, in terms of the trade-offs, general trade-offs between the performance and the ability to touch all the data. So here's the optical disk here showing a higher touch rate. And also, it's able to get some higher response time. And so this is part of why some people have seen this attractive with the right kind of configuration, like Facebook for storing images and that sort of thing. The magnetic tape tends to be not as high a touch rate. It's a very low-cost storage, and that's the curves it tends to make there. Now, this can be used to look at different sort of operations. For instance, you can look at performance for various sorts of tiering. In this case, we're moving a 1 megabyte object from hard disk drives to flash memory. So you got a PCIe flash tier with the hard disk drives. This 1 megabyte transfer is dominated by the slowest element, which in this case is the hard disk drive. So we're moving this 1 megabyte device, and it ends up being about 20 millisecond response time, and therefore a transfer rate of about 50 megabytes per second. you can operate on the smaller objects, which are more appropriate for the higher performance layer, and that's how you tend to do that. Since we're getting close to the time, I'm going to go to the interesting point here, which we can also look at for a given period of time. Okay, how much of the data on the actual drive can I look at? And this is where we get into this idea of this data event horizon. So it's important to have, for instance, if we're reading sufficient read-touch rate to extract all the data on the device within the given period of time you're looking at. So if you're below the touch rate, some of that data cannot be read back or written within the period of time in which you're talking about. So we've got a line here which is basically drawn where you're trying to touch everything once per month. So therefore it's 12 times in a year because it's a year chart. And so we can see here that we've got anything below that. For instance, if we have a 4 kilobyte objects here, the data on that drive is below the event horizon. I cannot access all the data on that drive. And this leads to another interesting point, which is kind of the reason why I called this thing. It is possible with the increasing size of storage devices and even systems that we potentially could be reaching a time when the data on the device or the system could be beyond the event horizon, the data event horizon. You cannot access all the information, either potentially either writing or reading, during the useful life of the device. So with that, I want to thank you all. If you're interested in the white paper we wrote, here's a link. I don't know if we'll put that up somewhere, but there's a link. You can get a free copy of that and take a look. Thank you.
We can take a quick question. You want to start?
Yep, sure.
Go ahead, Peter. I think Kurt's getting up to give the next talk.
The question that comes to mind is, I mean, that seems to be just about here now because we've got, there's 10 terabyte drives being sampled, and frankly, I don't think their maximum transfer rate's any faster than your 4 terabyte.
Well, in fact, the case of that 4 terabyte drive, if you had a terabyte objects, for instance, then or you end up with something like, it ends up being like 7 hours to be able to access all the data. And as it grows, that gets larger. So you're right, we're not that far away from this.
Yeah, our 8s in the lab are about 12, 15 hours to read the whole thing.
So we're close to the event horizon.
Yeah, and I think the good news, right, if I can make a statement since it's me, is that our touch rate,
Yes,
right?
yeah.
Even if we think about our personalizer, that I think about my personal digital data, right? It's in the 1/10% or
How often you actually touch it yourself? Yeah, yeah. All right,
Thanks.
thank you.
Thanks,
Thank you.
Okay, Kurt is next. Here's his particulars. Now you see it, now you don't.
Okay, so I think this qualifies as a crazy idea. The basic premise of this is that data center automation is a problem that I think is worthy of academic research in computer science. It's something that has traditionally been seen as a problem for industry to solve. Built-in assumption seems to be that computer operators and data center operators need to be highly skilled, and academia is focused on solving hard problems, and many data center outages are due to operator error. So if you think about the need for reducing improving overall reliability, obviously, to the extent that more automation can be introduced into data center management, it's a good thing. And having a human in the loop doesn't scale, particularly at large numbers. So the made me think of the analogy of self-driving cars. If you think about, for a long time, this was thought to be impossible, right? A crazy idea. And of course, recently, the realization has come that this, in fact, could be automated. And if you think about the needs of say, 80% of drivers are perfectly willing to let the car drive them to work, and so they can do other things. They don't need to be driving their Lamborghini stuck in traffic. So this is seen as a grand challenge, of course, for industry as well as for academia. And there are these contests and prizes and so on. And it seems like this is a hard problem, right? So the call to computer science researchers is to think about how large-scale data center automation could be fully automated. And so there has been work on various pieces of this. It's kind of a multidisciplinary problem. Control theory, there are people who've done work applying some of those principles. I think the thing that is particularly challenging that we see now is that data center scales are really increasing exponentially. We tend to add increased functionality into, say, our platform, and in general data center infrastructure is increasingly complicated, and the need for greater simplicity, radical simplicity, could really be, introduce a paradigm shift. So it seems that the time is ripe for addressing this in from a computer science perspective. I know that the drivers for getting tenure and getting papers published tends to lead to a certain focus on making important and very valuable incremental improvements in a number of key areas, particularly at systems level research. This is something that is perhaps higher level, but nonetheless it's a hard problem to solve. So I put that out there to the community. Steve.
So there's been a lot of talk in the last couple of years about cattle and pets in the data center. I wonder how you would think that principle applies here, because I can imagine if I think of cattle and pets in terms of self-driving cars, it'd be a lot easier problem if I treated drivers as cattle instead of pets, and I could just kind of like blow a few up if they, went too slow or went too fast. And I mean, that's kind of how I see the analogy to self-driving. So the question is, do you think that makes a big difference to the challenge of automation? I think when Brewer talked about this, he talked about at Google, they don't do things like process migration and so on. They just kind of kill stuff and then restart it. And that to me is a greatly simplifying assumption. So how do you think that factors into, I know VMware is serving legacy customers for the most part.
That's right.
Are you interested in automating their jobs or automating the new generation of cattle customers?
Yeah, well, actually, that's a great point, and that's where I think this 80-20 rule comes into play. I mean, there's great advantages to, standardization, uniformity, and so on. So there's a trade-off there, but I think that I like that cattle pets. Yeah. Ben?
I like the idea. Do you have a good example in mind of how you would apply control, or where you would apply control theory in a data center?
Well, so I think the one thing I should have mentioned is that this is really covering all aspects of data center management. So the initial configuration, which is always kind of a black art, where I think instead of having to send armies of consultants in to set things up in the first place. So the whole life cycle of configuration, control, monitoring, and ongoing management is really key. So I think the control theory aspects particularly come in terms of resiliency in the face of failures, in the face of changing demands, in the face of changing workloads, et cetera, obviously. But I think so starting with a kind of scoped problem space and building from there. I know there's been work on this sort of thing already, feedbacks, closed loop systems, but to really scale it up is a huge challenge.
Thanks.
Yeah.
Hi, Kurt.
Hey, Irfan.
Couple of questions.
Yeah.
So the analogy to self-driving cars is interesting. Most attempts that I'm aware of to solve that problem are these moonshot attempts that are actually remarkably multidisciplinary.
Yeah.
And academic research doesn't always,
Right.
have that. Even industry research is very difficult to accomplish that sort of a, wide multidisciplinary team
Yep.
to attack this problem. So 2 questions. One, to make this easier, do you happen to have a reading list or an agenda setting sort of a position paper that you'd be willing to write where you set out the challenges more broad, more deeply than you've had the opportunity to
right.
hear, where you actually talk about the existing work,
Yeah.
maybe even as a survey paper or something like that,
Yeah.
number one. And number two, is VMware doing a moonshot for this, and therefore you're kind of telling us about it, but you're just going to go out and do all this yourself and kind of left in the dust?
Yeah, well, I can't comment on the latter, but in terms of the former, yeah, that's a great suggestion. I actually got invited by Eric to do this about 2 hours ago to fill in for someone. So yeah, I'd be happy to give a more well thought paper. Sure. Mathi.
Okay.
Oh,
So a great problem, but this actually kind of frightens me because not because data center automation isn't a good thing. It sounds like a great idea, but you also seem to be calling upon the academic community to investigate this. And the problem with this is that there are very few academic research groups that actually have access to a large-scale data center, which is indeed
I knew
managing.
this was coming. Okay.
I'm actually fortunate enough to be one of the exceptions to that, but I don't know many of my friends who have.
Yeah.
And this leads to people doing research based on simulations and elaborate models which they've pulled out of thin air. And we've been here before. If anyone remembers mobile ad hoc networking, for example, and if you haven't blanked it. And that's not a place that academia really wants to go, because then you drift off into irrelevance. So the question is, how do you ground this kind of research? There are efforts in other areas, like sort of Planet Lab, for example, was an attempt to get people back to reality in some form. How do you get people to engage with reality in a problem like this if they don't happen to, have
this is where I think that's a great question, Mathi. I think that's really where a partnership with industry could really be instrumental. Yeah.
But just to point out, right, to be on the positive side a little bit, right, the grand challenge for the autonomous vehicles, right, that was DARPA eventually, they set up a course, right, and that was actually relatively important for the comparison of the thing. So you could imagine someone setting up a data center that they let your little autonomous thing
But the thing is that people could come up with their own plausible courses that other people would believe without, DARPA just standardized one, right? The point is that all you needed to do autonomous driving research was, a car and a large area where there were no human beings in the way to start with, which is why people like CMU managed to do this really quite successfully, relatively speaking. But the thing about this is, you need a data center with users.
Yeah, but it's true. But I remember. So when I was at Carnegie Mellon as a grad student, there was a couple of guys that did a self-driving car and drove across the country, right? And so 10 years later, the DARPA Grand Challenge thing came out. I remember, didn't those guys in the minivan already do the self-driving car?
But all they needed was a minivan, right? But here you need a data center.
No, I understand.
Someone else built the highways for them already.
That's right. But the government also has a lot of surplus data centers that they variously throw around, right? In all seriousness, right, the DOE, right, has made available some of their old things for storage research, right? So maybe there's some hope. But okay, so back on to. I need my opening thing. Oh, yeah, no, yours work fine. Yeah.
It works fine?
Yeah. Okay, so Munit is going to talk about the blockchain, and he's going to do it with PowerPoint or the PDF?
Hi, everyone. I'm Munib. I'm a final year PhD candidate at Princeton, and I also have a startup that is building stuff on top of the blockchain. For people who are not familiar, the very quick description is that you can think of the blockchain as saving global state of a system, and every node in the network has a complete copy of the global state. Sounds crazy, but this is how Bitcoin works. And you can look at it that whenever there is a change in the global state, which means a transaction going from one party to another, everyone gets a copy of that change as well. So you have revision history going back all the way in time to the Genesis block that happened somewhere in like 2008. So Bitcoin has been running for many, many years now, and the cost of attack currently on Bitcoin is around like $300 million. So a single party would have to invest that much money to buy ASICs and then try to take over the Bitcoin network. So once we have this public infrastructure available to us, what are the interesting things that we can actually do with the blockchain? And I was told that I'll have 4 minutes, so I have 4 ideas. There are many more that I'm happy to discuss later on. So the first is public key infrastructure. You absolutely do not need PKI centralized services anymore. You can just use the blockchain. And it's not just about getting certificates. I can actually, if I want to give Andy Tenenbaum access to my server, I can just say his username, and you can read his public key from the blockchain and add him to your server, right? And if any one of you want to go and grab his username, onename.com/AST, actually you'll see a message saying the name is reserved for him, and that's a message I wrote in the blockchain. And there's a username system that currently works. It's deployed and ready, so you can play around with it. The other interesting example is secure software updates. Whenever you have written software, you can actually sign it, and your public key can be read from the blockchain, and you can do automatic software updates. Next thing, decentralized DNS. People were actually crazy enough to try it a couple of years back. There was a fork of Bitcoin called Namecoin, and they implemented a decentralized DNS system with a new TLD, and actually got like more than 100,000 registrations on it. There were technical issues with it. We actually now have a re-implementation of that on the main Bitcoin blockchain. And the interesting thing is, interesting thing that I noticed was it gives you this very nice property of explicit cache invalidations. So I was running a bunch of resolvers, which would basically resolve a username to a profile data, pretty much like DNS resolvers. And every time there was an update, because the update can only come from the blockchain in a new block, I can actually just keep a cached copy everywhere and explicitly invalidate it. And that actually helped my job a lot. So it is technically possible to make DNS completely decentralized using the blockchain. The next example is a Sybil Resistance Dht. Over here, the example is that you can ask any participants of a DHT-based P2P system to give you proof of work or ownership of money. So I'll have to actually prove that I own a certain amount of Bitcoins, which is really proof of computation, right? That I've done a certain amount of computations, and hence I'm a real node, right? And you can actually pair it because the blockchain also gives you a sense of time. So you can also say that you need to have a transaction that actually happens X amount of time in the past, right? And combining these two together, what you have is essentially kind of like a gatekeeping system, but the gatekeepers themselves are decentralized because it's based on the blockchain. So you have a completely decentralized, some Sybil proof. Like I'm not sure if this is an actual solution, but I'm happy to talk to guys more about it, that to what level can we solve the Sybil resistance problem using the blockchain. And the last thing is that whenever I start talking to people about the consensus properties of the blockchain, the first question I get is, what about Paxos or Raft? Why wouldn't you just run that, right? What people need to start thinking about is that the Bitcoin blockchain is public infrastructure that is running, and you can just start building services on top of it, right? And furthermore, it's a global system. Anyone sitting in Australia, Japan, wherever, they are sharing a consensus state right now, right? So running a global consensus algorithm based on Paxos, I don't know that if anyone has tried doing it, but it does not seem like a very simple thing to do, right? And with that, I'll just open it up to questions. Oh, one last thing. Most of the development that we are doing on top of the blockchain is completely open source, and the development is also happening in public. So there's a public Slack channel, there's a public community, and all the code is on GitHub under MIT license. So any of you want to check it out, that's the URL.
So I have a question about the secure software update mechanism here. So a lot of major companies and major vendors have been broken into and had things maliciously signed with their keys, had attackers take control of their keys. So if this happens, and you have a bunch of deployed servers all over the place, and somebody goes and signs another blockchain entry, changing the key of the software to point to a key that they control, how does this system protect against it, or is this not part of the threat model?
Right. So one possible solution to that could be that you can actually restrict updates to that key, right? That it's basically giving a key value pair value, broadcasting it to the rest of the world, and you can say that don't accept any updates to this value.
So then when the attacker does compromise the key, how do you revoke the key?
So I think that basically starts getting into multi-sig transactions. So you can actually keep the revocation authority under a multi-sig transaction with multiple parties, right? So this is similar to how people are keeping millions of dollars in Bitcoins in cold storage, right? So you can use the same technology.
Anybody else? All right. Thank you. Thanks, David. Dave, I think we've reached you. Do you need some time to set up the? No, your beverage.
Yeah, well, yeah, because anything I'm likely to say is not going to sound very interesting if you're sober.
Okay, so Rick will pass out the refreshments if you make your way over there.
It's just Kurapa, so it's very light.
And just the poster session happy hour is just outside. There's no escalator, no stairs, so it's perfectly safe.
And I actually had to drive all over Sunnyvale to find somebody selling Kurapa.
Oh no, you didn't have it when you
when
you started the the idea.
Oh, good. I can even see what I'm supposed to say. Okay, so this is a system we're doing at Google, such is life. I put a name here. It's the Hikawi because so far the lawyers have knocked out the first three names that we suggested for one reason or another. So we don't know what the heck are we. So that's the name for the moment. That comes from F Troop, in case you're old enough to see to remember that. So, anyways, what we wanted initially was a system that would run everywhere. We're tired of having to learn new IDEs for every single piece of a distributed system that we're working with. So it's basically an open source RPC-based distributed environment. It's got an IDE for the RPCs. We are based, go down 3 lines, we're based on mostly written in Go. We have little jumps from Java. We call our RPCs from JavaScript by basically jumping into a local Go program, and same thing with Dart and with Java and stuff. But it's basically a Go-based system. We're not using Go's built-in RPC stuff, mostly because we had problems with it that that were insurmountable. I can talk about that some other time. The system itself has a malleable namespace. I'm a Plan 9 guy, the whole bunch of Plan 9 guys floating around. And basically, I was just trying to give myself a similar looking namespace, only without all of the problems. Encore Tali recently, at another conference, actually gave a talk on the security in the system. Basically, the system itself is as secure as we can make it. All of the RPCs are based on blessings. Blessings are essentially proofs of identity, much like signed certificates. The difference is they're extensible. So basically, you can add caveats to blessings, like, for instance, this blessing is only good for 3 hours, or this blessing is only good if it's confirmed by some identity provider. And in fact, you can, if you want to, you can always extend your blessing with some caveats and give it to somebody else. So the idea for us was we wanted to have things like Android phones or somebody coming in to use your network in your house and be able to say, okay, here's a blessing. Basically the way we're doing it right now is near field communication. We just tap phones, and here's the blessing so that you can now run on my network, and it'll work for a certain amount of time. At the moment, the stuff runs on only Unix-like systems. We've got it running on Android and Linux and BSD and those kind of things. Macs. But BSD is essentially Macintoshes. And this whole reason I'm standing up here is we're looking for victims. It's an open source system, but our lovely employer doesn't want us to release it as open source yet because we're using it internally, and he doesn't want us to embarrass ourselves where he is Larry. So we can't give it out at the moment without an NDA, but we can give it out. It's the eventual name of the system will begin with a V because we managed to get v.io as a domain, so you have to do it. So anyways, if you want to actually try it out or even take a look at it and see if there's anything in there you like, just mail me, p@google.com, and I'll send you back essentially a cookie so you can access all this stuff. All this stuff is on GitHub, so you can grab it all off of GitHub and play with it. The development environment itself for it is basically GitHub with Jenkins and Garrett and the usual crap. So anyways, that's it all. And get drunk.
Thank you. Any questions? Anybody? Comments?
Dave, is there a document describing the model and the capability, or is it just hacking through code?
Actually, there's a whole tutorial environment. Basically, once you have access, there's a number of white papers and documents describing the thing. Plus, there's a tutorial that walks you through using the different pieces of the system, the security and stuff like that.